Welcome. Let's explore e-commerce platform design, specifically focusing on Amazon-style scalability.
Imagine Black Friday. Millions of users flood Amazon. Latency spikes to 12 seconds, 40% of transactions fail. The database buckles under immense pressure, and the entire system threatens to collapse. This translates to millions in lost revenue and frustrated customers. Let's start with a naive approach. A single monolithic application handles all aspects of the e-commerce platform: product catalog, order management, payments, and user accounts. All these services directly interact with a single PostgreSQL database instance. This simple architecture quickly becomes a bottleneck. How quickly? At 5,000 requests per second, the database connection pool saturates at 300 connections. CPU hits 100% and query latency skyrockets from a manageable 20 milliseconds to a crippling 2 seconds. This directly impacts user experience, leading to abandoned carts and lost sales. The monolithic architecture simply cannot scale to meet the demands of peak traffic. One of the first steps to alleviate this pressure is introducing a load balancer. We can use Nginx or HA proxy to distribute incoming traffic across multiple instances of our application servers. This immediately addresses the CPU bottleneck by spreading the load. Let's say we add 3 application server instances. What does this buy us? Now that we've addressed the immediate bottleneck with the load balancer, let's think about asynchronous processing to improve the ordering workflow. Introducing a message queue decouples the order service from downstream services like inventory management and payment processing. With a message queue like Kafka in place, the order service simply publishes a message to the queue, and the inventory and payment services consume those messages asynchronously. This prevents the order service from being blocked by slow or failing downstream services. However, relying solely on the database for product information leads to repeated queries and increased latency. Introducing a caching layer between the application and the database drastically reduces the database load. With Redis caching frequently accessed product data, we need to ensure resilience and observability. We use Envoy in front of the cache to route traffic, Prometheus for monitoring key metrics, and circuit breakers to prevent cascading failures. Building on the resilience provided by Redis caching, we need to ensure our API gateway can gracefully handle failures and unexpected spikes in traffic. With Envoy in place, we gain the ability to implement advanced routing strategies such as canary deployments and blue-green deployments, which allow us to roll out new features to a subset of users before fully releasing them, minimizing the risk of impacting all users at once. To monitor the health and performance of our e-commerce platform, we integrate Prometheus, which tracks key metrics such as request latency, error rates, and resource utilization. Prometheus allows us to identify bottlenecks and proactively address issues before they impact the user experience. Furthermore, to enhance the resilience of our system, we can implement circuit breaker patterns. These prevent cascading failures by automatically cutting off traffic to failing services, giving them time to recover. Now that we've explored circuit breakers for resilience, let's delve into optimizing our data access patterns, specifically caching strategies, to minimize database load. Caching frequently accessed product details can dramatically reduce latency. With a read-through cache, the application first checks Redis for the product data. If it's a cache miss, the application retrieves the data from the database, populates the cache, and then returns the data to the user. This ensures that subsequent requests for the same product are served directly from the cache, reducing database load and improving response times. For cache invalidation, we can implement a time-to-live (TTL) strategy where cache data expires after a certain period, say 15 minutes. This ensures that the cache doesn't serve stale data if product details are updated in the database. Furthermore, we can use Kafka to propagate invalidate messages to our caching layer. To further optimize performance and scalability, we can leverage a content delivery network (CDN) for static assets like images and CSS files. CDNs store cache copies of these assets in geographically distributed locations, allowing users to download them from the server closest to them. This reduces latency and improves the overall user experience, especially for users in different regions. Now that we've explored CDN usage for static assets, let's shift our focus to dynamic content and the importance of robust monitoring for e-commerce platforms. To gain deeper insights, we can leverage Prometheus, which we configured earlier, to track key metrics at each layer of our architecture. These metrics include request latency at the API gateway, database query execution times, and cache hit ratios. Beyond performance, monitoring also plays a critical role in ensuring the availability and reliability of our e-commerce platform. By setting up alerts for critical errors, such as database connection failures or service outages, we can quickly respond to incidents and minimize downtime. In summary, we've built a scalable e-commerce platform using load balancing, database sharding, caching, and CDNs. Robust monitoring with Prometheus and Grafana provides end-to-end visibility. This architecture can handle high traffic and ensures a smooth user experience. But what if a major regional outage occurs?
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.